In this video, we'll continue to look at CSEC Physics past paper questions, right? Now, this question comes from May, June 2017, paper 2, question 6, and it deals with the topic of optics, right? So, we're looking at an optics question. Now, the question basically says that the first part of the question, part A, says using fully labeled diagrams, define the principal focus of 1, a converging lens, and 2, a diverging lens. Now, I've gone ahead and I've drawn the diagrams, of course, which you'd be expected to draw to use to define the principal focus of a converging lens or a diverging lens. Now, let's talk about a converging lens first. Now, converging lens, as the name suggests, converges rays of light or beam of light after being refracted. And so, therefore, usually a ray of light like this, let me just label this. This, of course, is the principal axis. The array of light, which is incident parallel to the principal axis, will be refracted so that it passes through the principal focus, right? So for a converging lens, when a ray of light, which is incident parallel to the principal axis, is refracted, it will pass through the principal focus. Now, for a converging lens, the principal focus is therefore said to be a real focus because the rays of light or the refracted rays of light actually pass through them. So based on this diagram, we could basically define the principal focus of a converging lens as the point on the principal axis through which a refracted ray of light which was incident parallel to the principal axis passes, right? So let me try to rephrase that or to word it better. The principal focus of a converging lens is a point on the principal axis through which a ray of light passes after being oh Lord. Anyways, so as I said, right? I'll try to word it. So as I said before, whenever there's a ray of light incident, so it is parallel to the principal axis, it is refracted so that it passes through a particular point on the principal axis, and that point, of course, is the principal focus, right? All right, so I think I have it now. The principal focus of a converging lens is a point on the principal axis through which a ray of light incident parallel to the principal axis passes after being refracted by the lens. Good, that is it, right? So I'll repeat it for emphasis. The principal focus of a converging lens is a point on the principal axis through which a ray of light incident parallel to the principal axis passes through after being refracted by the lens. Good? Right. Now, we also want to talk about the principal focus of a diverging lens. As in the previous question we did from 2019, of course, it required such, and I just basically left the diagram, right? So here we have a diverging lens, right? A diverging lens, and we have an incident ray parallel to the principal axis. So the incident ray is parallel to the principal axis, and upon being refracted and being diverged by this lens, it appears to come from a point on the principal axis, and this point is the principal focus, right? So for a diverging lens, the principal focus is the point on the principal axis from which a ray of light which was incident parallel to the principal axis appears to come from after being refracted, right? So after being refracted, this incident ray which was parallel to the principal axis appears to come from this point, the principal focus. Now, because the light ray only appeared to come from the principal focus, for a diverging lens, the principal focus is a virtual focus, unlike that of a converging lens, which is a real focus. So for a converging lens, this is a real focus, and for a diverging lens, this is a virtual focus, right? So basically, this is how we define principal focus of a converging lens and also of a diverging lens. Good? Right. So let's move on to part B of the question. Now, part B of the question says an object of height 7.2 centimeters is placed 18.0 centimeters from a converging lens. So once again, you have to pay attention to what type of lens we're dealing with. It's a converging lens, so that means it's going to have a real focus and the focal length will be positive, right? So we must remember that. A converging lens has a real focus and therefore the focal length is positive. A diverging lens has a virtual focus and therefore the focal length is negative, right? So in part B, we're dealing with a converging lens. Which of course implies a real focus, and of course that means the focal length will be positive. Now the focal length is given as 12.0 centimeters. So the focal length F, we put a plus sign for emphasis, plus 12.0 centimeters. The object is placed 18.0 centimeters from the lens, and therefore the object distance U is equal to plus 18.0 centimeters. And they want us to find, one, the image distance, right? So we're going to try to find the image distance V. And of course, in order to do that, we're going to use our lens equation, 1 over F equals 1 over U plus 1 over V. We make 1 over V the subject. And so this is a minus sign, of course, not an equal sign, minus sign. So substituting the values, we get 1 over 12 minus 1 over 18, right? Again, we could use our calculators, but it's a simple fraction, so we could easily find the LCM of 12 and 18 and proceed to add them as fractions. So LCM of 12 and 18, that would be 36. So 12 into 36 goes 3 times, 3 ones 3. 18 into 36 goes 2 times, 2 times 1, that is 2. And so this becomes 1 over 36. So 1 over V equals 1 over 36. And therefore, this simply means that V, the image distance, is equal to a positive 36 centimeters. So we must put our unit, right? So the image distance V is a positive 36 centimeters. Now, they also want us to find the magnification. So that's part 2 of the question, right? So let's do part 2 of the question here. The magnification M is equal to the image distance divided by the object distance. And once again, even if you get the image distance to be negative, when calculating the magnification, we disregard the negative sign and just use the magnitude of the image distance, right? So the magnification V, M rather, is equal to the image distance V divided by the object distance U, or we could say the absolute value, the magnitude of the image distance divided by the magnitude of the object distance, right? And so this gives us 36 divided by 18, which gives us 2. So the magnification is just a pure number, as it is a ratio of 2 distances. It tells how much larger the image is compared to the object. And so this clearly tells us that the image is twice as large as the object. It is twice the size of the object, right? They also want us to find the height of the image formed. Now, we were given the height of the object, which is, I didn't write it down, but the height of the object was given as 7.2 centimeters. So we can say the height of object equals 7.2 centimeters. Right? Now, and they want us to find the height of the image. Now, the magnification can also be expressed as a ratio of the height of the image to the height of the object. So similar to how the magnification is equal to image distance divided by object distance, then magnification is also equal to, let me write it down. So magnification is equal to height of image, HOI, divided by the height of object, HOO. And so therefore, if you want to find the height of the image, then you simply multiply the height of the object by the magnification. So therefore, this means that the height of the image, HOI, is equal to magnification times the height of the object. And so this gives us 2 times 7.2, which gives us 14.4 centimeters, right? So therefore, the height of the image is 14.4 centimeters, since the height of the object is 7.2 and the magnification is 2, right? Part 4 of the question asks us to determine whether the image formed is real or virtual. And that is fairly simple. The image distance is positive and therefore the image is real, right? So generally, as I said before, we use a sign convention, real is positive. So if you're calculating the image distance and it works out to be positive, then that means the image is real. However, if it works out to be negative, then that means the image is virtual. And of course, that is provided you do your calculations correctly, right? So for instance here, if you had made a mistake, and instead of 1 over 12 minus 1 over 18, you made a mistake in substituting the value of f and u, and you got 1 over 18 minus 1 over 12 instead, that would have worked out to be negative, and that would have meant that you would have misinterpreted the result. Well, no, not misinterpreted, but the result would have been incorrect. But if you had went on to say the image was virtual due to v being negative, then the answer would have been incorrect, but you might have gotten the mark given that your interpretation was correct based on an incorrect result, right? So once again, if you had made the mistake and transposed these and gotten minus 36, then you'd have probably come to the conclusion that the image was virtual, but that interpretation would have been correct based on the minus 36, but it would have been incorrect based on what was expected from the question, right? So, the marker might have been lenient, or CSEC may be lenient and give you that mark in a case of error carry forward, right? But of course, you don't want to be making such mistakes, right? So this question was, May, June 2017, paper 2, question 6.